So our first speaker for the session will be Dr. Jake Bleacher, talking about HEOMD enabling research across the human exploration architecture. Take it away, Jake.
All right, Kelsey, just check. Can you hear me?
Loud and clear.
Awesome. All right, thank you. Thanks, Kelsey, for moderating the session. And I think that everybody's seen, if you've been participating so far today, you've seen a good bit of information about what our plans are moving forward as an agency for Artemis and exploring the moon and moving beyond low Earth orbit. You saw the talk before mine. Julie Robinson talked a little bit about how HEOMD is organizing itself in order to meet the objectives of Artemis. And so I'm going to go a little more detail into how the Artemis approach for HEO is working to enable science as well as technology demonstrations as we move forward. Next slide, please. So as Julie talked about, our job inside the HEO Science and Technology Utilization Office is to understand the objectives that our stakeholder organizations bring to the table, which includes SMD and STMD, but other potential partners as well. Understanding the objectives helps us decide how to design that architecture and what the requirements will be on that hardware. And so when I talk about that hardware, this is kind of our Artemis snapshot image here. We've got the transportation on the left, the SLS and the Orion, which is in development in the Exploration Systems Division. And then we have the surface elements that would include the HLS, the Human Landing System, future rover concepts, habitats. Working along with that will be in orbit. We have our gateway that will serve as that platform from which we can both study the deep space environment as well as enable access to the lunar surface. All of that coupled with the commercial lunar payload services that Joel and others have talked about already. And I like how he pointed out earlier, when we show our HEO stuff, it kind of all hinges on these early CLIPS payloads that we're sending, because that's really where we have the opportunity to be global early on. And so as you've seen from some of the information earlier, the CLIPS landers are going to a bunch of locations. So we'll have an opportunity to take what we're learning at the South Polar region with our astronauts and have a better global perspective to apply that and understand the moon as a whole. Next slide, please. So I wanted to show this slide for those of you who maybe were participating during the Lunar Planetary Science Conference. While we had our NASA session there, we were right in the middle of the Green Run hot fire test for the core stage of the SLS. So between that presentation and now, we were able to add one more green check to the series of tests that we need to run in order to meet Artemis 1. And so this will be our first mission to test our crewed capable spacecraft flying out to the moon and coming home. And so Artemis 1 is a critical mission for us in making sure that we can get our astronauts to the surface of the moon. Next slide, please. As we move along that path, I think Kathy did a good job early on of showing how both science and technology demonstrations go hand in hand with all of the hardware that HEO is developing for our Artemis architecture. The SLS has the capability of deploying up to 13 secondary payloads or CubeSats, and it's great that at this point those are all occupied for Artemis 1. And so here's a series of payloads that will be delivered by the SLS, and you can see here there's quite a diverse range. There are some payloads that are going to be going to study the moon itself, but we're looking at propulsion demonstration. We're looking at interacting with asteroids. We're looking at other aspects, testing, biosensors and activities like that. So you can really see there's a diverse set of objectives that we can hit working together with both the space technology and the science directorates as we move forward. Next slide, please. Coupled with the deployed payloads, secondary payloads, we also have pressurized payloads. So we're going to be learning about that environment within the Orion as we move forward. And so, a phrase I've always liked to use is that science and technology are basically our lifeline for survival. Several folks have kind of brought this up as well earlier today. That information we get from technology tests and from the science observations we make really helps us understand the environment within which we hope to survive and thrive as we move forward with Artemis. So just pointing that out here that that first Artemis mission, it's not only a tech demo of the hardware to land go to the moon and then eventually land, but it really is going to be collecting data for us to help us understand how to survive throughout the entire Artemis program. Next slide, please. We've talked a good bit about Gateway. I will just kind of reemphasize here. Both Kevin Sato and Jim Spann earlier talked a good bit about the value of Gateway from a science mission directorate perspective. This is a great example of how we identified some early payloads that we were able to quickly organize and get ready to fly with the early Gateway elements. Ursa and Hermes are both studying kind of that deep space environment. They'll give us a sense of what that environment will be like that both our hardware and our crew will have to survive in. And this is all critical for us understanding, what we will deal with as we stay in the lunar vicinity for longer periods of time, moving forward with Artemis and prepare to go on to travel elsewhere in the solar system. Also note here, internally, we're looking at some ESA internal dosimeters that could potentially tell us not only what that environment is like outside the gateway, but what is it like inside the gateway. And we can couple that with the dosimeters that we'll have on the inside of the Orion on Artemis 1 to really start to give us a sense of what we're dealing with in that deep space environment as we explore the moon. Next slide, please. So this is an artistic rendition of what an Artemis base camp might look like. And this is kind of our goal as we move forward down the road, is to continue to increase our capability at the moon, to bring new elements that enable us to do more science, to test more technology. And so we'll have a number of elements. And I think it's really critical to point out the link between the three directorates as we go through this process. They're all intimately intertwined in enabling us to take advantage of what we have at the moon, to enable us to explore more and for longer distances and longer periods of time. Next slide, please. So this slide, we want to highlight that there are a number of key elements that are of value, not only to exploring the moon, but exploring in deep space. The really important aspect to understand here is it's not just about exploring the moon or exploring Mars. There's key elements that are foundational to how we explore in deep space. This includes an integrated strategy involving ISS, involving our commercial crew in low Earth orbit, extending that to the moon, eventually extending onto Mars. But the same hardware that will enable us to survive a trip to Mars will also enable us to survive for longer periods of time on the moon. So I want to emphasize that this is all key infrastructure that's needed to help us extend our presence on the moon, explore larger areas, explore for longer periods of time. All of that's foundational to us continuing to do cutting edge science on the surface of the moon as we move forward. Next slide, please. The human landing system is kind of the big piece that we're working on right now. This will be our first commercial landing system to take astronauts to the surface of the moon and back to lunar orbit. So this is that piece that will get us down to the surface, and we'll be testing that out with our first crewed landings for Artemis. Next slide, please. We've been talking about the human landing system a good bit over the last year. For those of you who have been closely paying attention to this, last April we put out our base period. Selections were announced that brought 3 companies into competing. And we've slowly been working on that over the last year. A lot of folks working really hard to get to the point where we recently announced SpaceX was selected for option A. I think it's important to note that option A for SpaceX is for a test demo landing, non-crewed, and 1 test demo landing with crew. There will be opportunity for basically a service contract following this that will be leading into repeat landings in the future. So I just want to be clear about what it is that we have recently selected with the human landing system. Next slide, please. So now I want to get a little bit into more of the formulation and the planning and strategy aspect to this. As Julie highlighted, there's really some cross-cutting capabilities that are important to how we can achieve the objectives that our stakeholder organizations have. For instance, understanding that to do the science that we want to be doing on the surface of the moon, that requires mobility. We want to be able to get farther and farther away from the spot where we land. Initially, that will start out with our cruise landing and walking around on the surface during our test demo landing. But then we plan to quickly bring online an unpressurized rover, Lunar Terrain Vehicle, or LTV. So the objective there, again, is to help and continue to increase the range at which our astronauts can explore. We're looking here at reusable, rechargeable vehicle that can last for multiple missions. So we want to be sure we're sending that to the location where we're going to be conducting repeat landings. So unlike the Apollo lander, which was their rover, which was there for only one mission, this would be something that gets reused over and over. And so that's part of that. We kind of talked about what does sustainable mean. Sustainable in some regards means having elements that can be reused. And so this is kind of one of our first steps in that direction. HLS that can get us, land us multiple times. Rovers on the surface that we can take advantage of for multiple missions. Next slide, please. Now, eventually, we would like to be able to travel even farther away. And so many of you have been working on concepts over the last decade or so, or even longer, about pressurized rovers as well. So an unpressurized rover grants us access to moving around a good bit more than we could if we were just walking, but a crew member still has to wear a suit during those EVAs. Whereas a pressurized rover is basically a mobile, habitable environment. So now a crew member or two crew members can drive a vehicle like this in a shirt sleeve environment, and that really extends the range over which we can explore. So again, these notional concepts that we're developing here as our architecture strategy, that we're really pointing at, being able to reuse elements as well as extend our range that we can cover, extend the amount of time we can be there, and increase the capability throughout that effort. Next slide, please. To go along with that, we're also looking at concepts for foundational surface habitats. So just like we would like to have a mobile habitat, we also kind of want to have a base camp, a place that's kind of home when we're on the lunar surface. And so coupling a surface habitat with a mobile habitat really increases the capabilities of what we can do on the surface. And so the point I really want to drive home is, the mobility enables us to see more, to go more places and bring more back. A surface habitat may be used in order to potentially store samples, store hardware, payloads that we want to reuse more than once. If we get to the point where a payload we take to the surface could be used over multiple missions, we'll need places for them to stay, potentially recharge. These are going to be things that we can start taking advantage of on the surface between habitat, a mobile habitat with a pressurized rover, and an unpressurized vehicle to increase our capability. Next slide, please. Meanwhile, in addition to the initial capabilities at the gateway, we're looking at elements that will increase our ability to stay longer in orbit. And so this, again, is a really critical part of us understanding longer duration stays in the space environment. So we're considering options for habitation test elements that could be connected with the gateway and have, as we point out here, up to 15-year lifetimes. So we could have multiple missions up at the gateway taking advantage of these as well. As I said earlier, this helps us prepare for the trips we may take to Mars, but it also helps us prepare for longer duration activities in the lunar vicinity. So again, these are the capabilities that we're considering moving forward to help us prepare for ever increasing activities at the moon. Next slide, please. And so I just bring it back around to the slide again to re-emphasize, what we're talking about is a buildup of capability over time on the lunar surface. This helps us prepare for exploring more of the moon, getting more science to the moon, more technology demonstrations. As Kathy really emphasized early today, we are going to learn as we move along. Some of the decisions that need to be made for this architecture have not yet been made because we're going to learn from clips. We're going to learn from our first landed missions what it is that we need to do in order to gain more and more access to the lunar surface. and then prepare for longer duration activities in deep space and onwards to Mars. So again, this is a multi-directorate effort, collaboration inside NASA. And again, I want to thank everyone who's taken part in these LSSWs over the last year. The reports that have come in from these workshops have been really beneficial to us as a means to make sure that we're considering what the community is thinking about as well. So please do take advantage of the Lunar Surface Science workshops moving forward. With that, Kelsey, I think I'm done, and thank you.
Thanks, Jake.